All right. All right. So, yeah. So all of the packages are available in R. So that'll be good. All right. So, just gonna move. Okay. Just to remind you, the difference between linear and nonlinear models. I think we're all familiar with the linear models, but there's definitions that Bates and Watts give in their 1988 book on nonlinear regression analysis, and essentially it pertains to the. Excuse me, I gotta let people in again. It pertains to the derivatives of the equations they're exploring. And for a linear model, when you take the derivatives to solve for a particular parameter, none of the other parameters or the parameters are in the derivative. And if you remember, if you ever studied the nonlinear model derivation, you can see that you can actually, if that definition is correct, you can actually solve the parameters by hand. So they come out where there's actual solution that you can get. Whereas in nonlinear models, and here's Bates and Watts definition, at least one of the derivatives of the expectation function with respect to the parameters depends on at least one of the parameters. So if you have any questions about whether an equation you have is a nonlinear model, you can actually use this function in R called derive3, where you can input your equation, give it the parameters you want to get the derivatives for, and then run this, and you can actually, from the information that spits out, you can actually find the derivatives for each of those parameters. And focusing on just the first one, you can see that for the derivative for the expectation function with respect to L infinity, there's a K and a T0 there, which you don't know. So you can't solve these by hand. So we have to use numerical methods. For instance, the optimization algorithms that you can use in R to solve that stuff. And in order to solve them, we're going to be minimizing some objective function. And one of the most popular, I guess, are using least squares to fit models. So you're taking your equation, providing initial parameters, using some type of optimization algorithm. You predict a fitted value. It compares it to the observed values. Sum all those across the observations, and that would be at least some of these squares and some of the squares, and then the algorithm just keeps searching until that least squares function is minimized. And the common function or package, no, this is a function in R, is the NLS function, which is the nonlinear least squares. And that's, you don't have to call that, it's in the base package. The slides actually move here. There we go. So one of there's lots of assumptions, just like linear models, when you are fitting models to data, and the nonlinear regression models are no exception. And these models, you have the primary deterministic functions, which you're trying to fit, which in our case would be playing around with the von Bertalanffy growth curve, which is above. And then the stochastic part, which are the error parts, are assumed additive, so that your observation is a combination of the deterministic part and some error. And those errors are assumed to be IID, which is independent and identically distributed, which means that there's no correlation in the errors, and also that each has the same probability distribution, and all the errors come from a normal distribution, which has a mean of 0 and some variance, which is equal across the errors. And usually to verify these assumptions, we use some types of, once we fit the model, some types of residual plots. There's other things to do, like you could test the residuals for normality and all those things. And I'll show you a few of those things. So the most common function is this NLS function. It minimizes by least squares, and of course it assumes normality. There's a number of this couple of optimization algorithms that you can use, and the default is this Gauss-Newton algorithm, and don't ask me the difference. And this does calculate, when you put in an equation, it will calculate the derivatives within the model. So then it uses that information to find the minimum. And like all nonlinear models, you can actually have global and local minima. So it's best to explore different starting values with anything. Whenever you run these models or estimate the parameters in models, and try a bunch of different starting values, make sure you get to the same global minimum. And of course, this NLS does generate a lot of information on residuals, so you can use those to check model fit and assess whether you're meeting your assumptions. Oops, hold on a second. So all right. So this is just an example, and this is in the code I sent out this morning, just some brief examples. And I simulated some fish, and I gave you that code in the script file. So you in NLS, you're setting up a model where you have to the left side of the tilde formula symbol is your just I'm gonna mute everyone here. All right. To the left of the tilde is your dependent variable. In our case, it'll be some length observation. And then you set up your equation, where here we have L infinity K and T sub 0, the parameters of interest that you want to estimate. And then you'll have your independent variable, your predictive variable. In this case, we have age. You can, in NLS, you specify your data frame that you want to pull the data from, and then you need to provide starting values to help estimate those parameters. So in NLS, you use the start equals, and then the parameters are in a list, and you can provide those. And then you run it, and then you can look at different parts using the summary functions. And in this case, you get, the standard output with your parameter estimates, standard errors, and then it tests whether those parameters are different from 0. And this is, in this case, it's just this for a simulated fish. I call it the widget fish for nothing. There. Hold on a second. The big, oops, damn, back there. The big assumption, of course, is in these, oops, going backwards. There you go. There we go. The big assumption is in these models, just like linear model, it assumes that there's a constant variance across the levels. And so one thing we need to do in nonlinear models is to look at the residuals for patterns in the residuals. And this graph's right below for this example. And you can plot both the residuals against your predictive variable or against the fitted value, which is actually the recommended way of doing it, using the fitted value. And you can explore whether and examine these graphs to determine if there's any type of pattern. And nothing's perfect, but in this case, it seems to be about the same variance going across the levels. So we could conclude from that we're probably not violating the assumption of homogeneity variances. And of course, we can then test for normality in the residuals. In this case, I just plot the residuals in a histogram, and you can use the QQ norm and QQ line functions to examine whether they're normally distributed. And without getting into what it means, all you have to do is look, use those QQ norms, and if the points lie on the line, the distribution is pretty normal. But if you see these huge skews in the pattern going away from the line, then you probably get a problem. And in this case, I also tested whether the residuals are normally distributed using the preferable Shapiro-Wilk test. That seems to be the best test in the literature for determining normality. But keep in mind, if you have fewer than 50 observations, then the ability to detect any differences really drops. So what if you do have heterogeneity of variances? And in fish, I think this is probably a bit prevalent. In a lot of simulations work that's been done with growth function stuff, they always assume a constant CV across the ages, which means that you have your variability, the variance increasing as the age increases. So what happens if you don't deal with this? So in this case, I just fit this same model using the NLS function. And once we check the variances plotted against the residuals fitted against the plotted against the fitted values, you can see that there's definitely a problem here where you have increased variance in the residuals as you're increasing with the fitted value. And you do see that somewhat at the beginning in the left-hand plot where you're plotting residuals against age, which if you have a lot of plots, a lot of points, it could, using this residual versus age plot can actually mask some of the patterns. So that's why they recommend you always examine the residuals versus the fitted plots. So yes, we have to fix this because it violates the assumptions. And we can go ahead and test again and plot the residuals, and you can see there's deviations from normality here, and the test even concludes that yes, you don't have normal distribution in your residuals. So what are the consequences of not fixing heterogeneity? Well, I did some simulations where I had the true value. I had developed observations that have heterogeneity present, and there really is no impact on the parameter estimates, but there is impact. You see on this graph, on the left, I was looking at present bias from the true values, and the upper graph is for the parameters themselves, and there was really no bias if you don't correct the heterogeneity. But there is in the parameter estimates, even though it's not perfect, you still get, once you correct, you still get a little error in the standard errors for those parameters. But the big thing that it can influence is the correctness of any type of model comparison. So I found this little quote that says, if group sizes are unequal and homogeneity variance is violated, then the chi-square statistic, which is basically what you'll be using to test growth curves, we'll get to that later, will be biased when large sample variance is associated with small groups. And so what this can do is essentially inflate your type 1 error, which means you will be detecting more frequently. You'll find differences in comparisons more than there should be. So that's why it's really important to fix heterogeneity if it's detected in your data. So how can you do that? Well, there's several ways. The first is assuming that you have heterogeneity. Basically, that's also known as having multiplicative errors within the data. So you can fit a Bonnebert model that has multiplicative errors. And the way you would do that is you need to transform your observations onto the log scale, which adjusts the equation that you're fitting so that the errors do become additive, but you're actually minimizing the sum of squares of the logs of the predicted versus the observed values. And you can see here down below, when you do that in this example, it does correct it. There's still a little bit of stuff, but nothing's perfect. You can do this type of stuff in the NLS function, which I gave you the code for, but also in my fish methods package, I have a function called growth, which all you have to do is change an argument, and it'll change how the models will fit to your data. So you don't really have to do any what do they call it? You don't have to fix like transform before you put your data in the model. So that's available, and I gave you the code for that too. The second thing you could do is do what's known as least squares. In this case, since you're assuming that the errors are independent, but they're not identically distributed, meaning that there's a relationship within those residuals. Oops. And what you do is actually take the you would fit the von Burt model to your means, the mean length at a particular age, but then you weight the observations by the inverse of the variance of those means, which is essentially the inverse of the standard errors squared. And weighted least squares, the weights, these weights 1 over the variance of the means are generally assumed to be known, but we don't know what the true values are, so we have to estimate them. And that's where this kind of method can become problematic if you have small sample sizes, because if you have low sample sizes, those weights can be all over the place and can affect the results. And so in this method, if the variance about your mean length at age is large, then those points get less weight in these. So the more information in it at a particular point, the more weight it gets. So you can do that, and you can fit weighted least squares in the NLS function, or again in my growth function that's in my fish methods package. So you can, it's just another model. You can just change an argument to fit. You don't have to do anything. The third way, which is becoming my favorite way, is to actually model the variance structure of the errors. And this is a neat function that's in the package NLME, which is the nonlinear mixed effects models package that Doug Bates and I forget his other guy's name, Pinheiro, produced, and it's in their book Mixed Effects Models in SNS Plus, and it's in chapter 8 in particular. And the function that that you can use to do this type of stuff is known the GNLS, which is generalized nonlinear least squares. And unlike the NLS function, where you assume all the errors are independent, etc., and the GNLS, you can actually have a correlation structure within your residuals. And in the weights function, this is where these model structures will be modeled. And in our case, up above here, we'll particularly use this function known as the power function, where the variance becomes a function of the fitted value with a parameter theta here, I think it's theta, that you're estimating. And what's neat about this, it provides a framework where you can actually compare nonlinear models with and without correction for the variance and stuff like that. So you'll be able to tell whether the addition of this model variance structure actually improves the model fit. So it's very similar to all the way you compare linear models in R and stuff. So the instructions for using GNLS. So first you got to download the NLME package. And Pinero and Bates recommend that you actually create essentially a start function for the model that you're creating. And the way to do that is using that function I already mentioned, using the deriv3 function where you can input your model, what parameters you want the derivatives for, and then this x here will be whatever independent variable, the predictive variable you're going to put into the model. In our case, it'll be age. And what this provides is just all the derivatives for like each of the parameters which are in these dot grade functions. You see dot grade k, dot grade t0. These are the derivatives, and then you have to match up here with these different expressions. And provides the equations for the Hessian, which is when you invert it, you get the standard errors. The variance covariance matrix from which you can then get the standard error. So I guess this is a way, from what I understand, is a way of making this solving for parameters a little bit faster. So it's really pretty simple to do, and we'll be using that example this kind of form in the examples coming up. But you can in GNLS just input your equation, but Pinero and Bates recommends that you do it this way. So once you do that, you have to pick the variance function, and there's a number that they provide, but for our purposes, and it seems to be the correct functional form is using this fair power function, which I just showed you back in the other slide. So that's the variance is changing as a function of the predicted values or the fitted values raised to theta here, which is an estimated parameter. So in the model, which we'll get to, this is the form for the variance power. You can provide starting values in the value argument, and then you stick in what predictors or even covariates that you can use to fit the power function to the residuals. And so in our case, we just wanted the fitted values, but they have a lot of different cases where in their book where you can actually use other things, like if you had temperature and stuff, for some reason, I don't quite understand their models, but you could include those too. But in our case, we wanted the fitted. You want to use the fitted function here. So the form, variance power form, is this form equals tilde fitted with parentheses and a dot. So that references the fitted values that they're using in the model. So you can also, you don't always have to fit that theta parameter. You can always fix it. So if you do a value or something, you could, as the lower line shows, you can enter a value and it won't be estimated. Oops, wrong way. So, so I'm just going to show you quickly, how the function looks, the way you set it up to include that variance power function in. So this next few scripts are in your the script file that I sent. So up above here, you see the GNLS function. I have the TL, which is total length for this particular fish, and then that derivative function that you essentially set up. And so you input age here, and you're going to be estimating L infinity, K and T sub 0. Give it the data set. There's the control. So if you need to control, how many iterations are done, the maximum you can change, and a bunch of the relative tolerance, all these things. And then you need to provide, again, starting values. So here I'm providing it data that's has heterogeneity, but I'm just fitting the standard. And you can see the graphs on the left here, right, that you do have heterogeneity, so you need to fix that. And so the way to do that is you use that variance power function within the weights command here. You don't need to provide a starting value, although you can, which is the value equals up here. And so you just run it normally. In the output, when you do a summary plot, you'll see the parameters up above here. You'll see the estimated that theta value, I guess, the 1.35. So, and then it corrects for that using that equation. And on the right, you can see the results of the on the residual plot showing that pretty much fixed the problem. So, as I said, you can use these the GNLS functions just like you would in model comparisons like linear models. So here, use the ANOVA function, which I didn't plot here. But anyway, you would use the ANOVA small case ANOVA, specifying first the model with the most parameters. Basically assumes that the following models are nested within those, although the order kind of doesn't matter. But in this case, you want it just for order, keep the one with the most parameters on the top, which means it's entered first and then ANOVA parameter, then the second, and it'll calculate the log likelihood ratio test and whether it's significant or not. And yes, including this error function, modeling the error function does improve the model fit. So you would keep that in. So all of these, up to this point, it assumes all your data and stuff were collected correctly, you know, having individuals collected randomly and all this stuff. But that tends not to happen in the fisheries world. And often people will collect age and growth, length and age data, or length and then the fish that they'll age using some type of stratification sampling. So in many cases, people will decide beforehand that we want to collect X number of fish per 2 centimeter length bin, and then age those individuals. And that type of sampling, because you're not, most people then just take those observations, stick them into a growth model with, once they're aged, and come up with growth parameters. And the problem with that is you're not correcting for the sampling scheme that you're using. And all of those, and not doing that will provide very biased, it can provide very biased estimates from your growth model. And this on the right here is just, this is part of that paper I'm trying to work on, is looking at the different von Bert parameters across the top will be the columns, and going down at different levels of variance in the models. And then the different symbols, the open symbols are when you proportionally sample out of the different trawls that I'm simulating. And then the blacks are when you're using a length stratification. And you can see in a lot of cases, depending on how many ages you're collecting, if you're getting them correctly over the whole age span, you can see this can be lots of bias in those parameters. So this was recently noted again by Goodyear in 2019, and in 2020, Andrea Peralt and Noel Cadigan out of Canada published a paper on how to estimate growth curves parameters when you are using length stratified sampling. There's no function in R for doing this, but they programmed their models in TMB. And I got the code recently from Andrea, she sent, and I'm going to try and get that into my fish methods package. I've been trying. One of the problems with having a package on CRAN is that your code has to be portable across all operating system platforms, so like Macs and Linux. And having TMB, you actually have to compile the once the package, your like fish methods is installed, the package would automatically compile the C++ file from TMB and it'll become part of the code that's implanted on your hard drive. Unfortunately, I've only been able to figure out how to do that for Windows, but I haven't been able to do it for the other platforms. So it may take me a while. But in the meantime, I did create a function that will do this, but at a very slower, the fitting is very slow compared to TMB. So that's available. So if you ever do this type of sampling, you should probably be using this method. And then another paper recently, well, 2014, that's not recent, but just to point out, if you're not collecting your fish appropriately, there may be some types of biases associated with, selectivity and things like that. And Amy Schuler and others down at the NIMS in North Carolina published a paper in 2014 where they developed methods for estimating, for correcting for gear selectivity and availability. They programmed there as an 80 monitor builder, and it's pretty straightforward. So you should be able to program that in R using the Optim or NLM MinB optimization functions. So, and I was looking at the likelihood, and I think you probably fit in a power function in there to correct for any heterogeneity, if there is any. And then I just want to mention also there's, one of the assumptions is that our ages are estimated are known without error, but we know all aging information is otherwise. So Jason Cope and Andre Punt published a paper in 2007, and they showed how to model aging error using random effects models to correct for that. So just want to make that people aware of that. So you could probably get the code from them. They're pretty friendly. So. All right, so the last few examples I showed or assumed that everything's correct. You're not doing any type of length stratified sampling or anything. Everything's corrected properly. So and that's the case, then you can go ahead and start looking at comparing parameters across different group structures. For example, like if we were interested in comparing growth curves between sex and a species, then you're okay to do that if all the assumptions that we mentioned before are appropriate. So the historical paper that that started allowing group comparisons without really getting into multivariate crap that went on in the early 80s and stuff like that was Kimura's 1980 papers published in Fish Bulletin. And essentially he showed that the likelihood ratio test is the best method, and it was followed up by several papers after that by Serrato in 1990 and Kimura again in 1990. All these methods, as I mentioned earlier, have the same assumptions. The errors are independent, normal additive errors, no heterogeneity up to this point. And then there's equal population variance across the groups that you're comparing. So other term for that is the within group variance is the same across the group. So you have to be careful with that. So he showed how the likelihood ratio test is used, and the way this works is you first start with a full global model. So let's say you have two groups, males and females in this case. So, and you're interested in whether the parameters, any combination of those parameters are equal or not equal across the groups. And the first thing you start off with is providing a fully parameterized or the global model. So if we have two groups, there'll be a model where you're estimating 6 parameters, L infinity, K and T sub 0 for each group. And then you'll have an alternative hypothesis likelihood where you, for instance, assume in one case like L infinities are the same between the groups. And using, so the full model will be in here designated as omega, and the alternative hypothesis is, I can't remember the name of that symbol, the W. So the likelihood ratio test looks like this, where you're taking once you do your fit, we're using least squares. You're taking the residual sums of squares of the global model, dividing it by the residual sums of squares of the alternative model, and calculating a likelihood ratio based on this formula. And then the likelihood ratio has a chi-square distribution, and you calculate degrees of freedom by taking the difference between difference in the number of parameters between the two models. That will be degrees of freedom, and you can test whether those are significant. So if they're not significant, let's say in our case, the RS omega and RS SW are pretty close, then you won't get significant results. And that means that the alternative hypothesis is actually the better model, since the full model, the residual sums of squares didn't really change. So that's how I would use that. So in Kimura's paper, he provided formulas for doing different types of least squares. So in the simple case, the first variance assumption was just the standard least squares. We do the observations minus the predicted, and then he provided an equation for doing the means, just singly the means, and fitting the model to just the means. And also, as I discussed earlier with the weighted least squares, he provided an example of that. So you can use these different types of models to and test against the different groups. And so I'm going to give an example in my fish methods package. There's a data set called Kimura, which it uses in the 1980 paper, so you can use that if you want to follow the example. And so what I'm going to show you is just first how to do it in the NLS package, okay? Function. So what you're going to do is first is here's the data from Kimura. What you're going to do is set up and create another variable that's actually just an indicator variable of one group. So in this case, we're interested in we'll be interested in estimating parameters for female and male. In this case, I'm going to just say, well, the males will have a 1 when this parameter is turned on, and it'll be 0 when the parameter is turned off. And I don't know if that makes sense, but hopefully this will. And the way the model is set up is you'll have a base parameter like this L infinity. So that will be the base. And then for the, and this is the two group case, L infinity this L infinity represent the L infinity for that first group. And then there will be an estimated deviation from that parameter, which will represent the parameter for the second group. But you then, once that's estimated, have to add this value, this B1 here, to the L infinity to get the L infinity for that second group. I hope that makes sense. So in this case, the second parameter will be associated with the males. So when this S is 0, then essentially you're estimating the parameter for the females. But when it's 1, then it's L infinity plus B1 times 1, which will give you, the sum of this will give you the parameter, L infinity parameter for the males. And the same thing for the K and the T sub 0. So this is the way it would look like if you used the NLS function. you'd set it up here, you'd be estimating B1. You have to provide an estimate for that. And since it's a deviation, it would be lower than the actual L infinity that you enter. B2 will be the difference for the K, and B3 will be 1. So you can run that. And you, again, this is how you would code that S in the function. And then you do that. So this is still Kimura's thing, and we do that for alternate hypotheses. So in hypothesis 1, we're saying that the L infinity 1 and 2, there's no difference. So then you just have that L infinity as a single parameter in this model. So down here, it's just L infinity, and you have to get rid of the B1 here because that's no longer estimated. Then we can say hypothesis 2, we're wondering if the K's are the same. So again, that you eliminate that, and then T sub 0 down here, eliminate that. And then the final model will be basically fitting a single model to all of the data. And then the way you do the likelihood ratio tests, and I provided the full code for you in the script file, is to then get the residual sums of squares, which you can get just by using the residual function on the output object, and then calculate the difference in the log likelihood ratio test using the global model RSS and then the alternate model RS in the denominators, and then calculate degrees of freedom and then the chi-square significance. And as I mentioned earlier, if the residual sums of squares for the alternative model is greater than the residual sums of squares for the global model, then less is accounted for by that alternate model. And if chi-square is significant, then the global model is the better model, so you would keep that. So in the case, oh, sorry, let me just finish this. And then if it's not, then the alternate model is the better model. And so here's just a summary table, and this is found right in Kimura's paper, 1980 paper, showing you comparing here the full model to the model that assumes equal L infinities, and they're different. So L infinities, there is a difference in L infinities between sexes. And then the K comparison, it's very borderline. So it's up to you how you conclude that. But keeping in mind that unless you have lots and lots and lots of samples, there is an issue with chi-square is asymptotically, sample sizes can affect the power of the chi-square. So remember that the test is approximate. So if you have borderline values either below or above, let's say you pick 0.05, then you have to think about whether that's actually significant or not significant. And then in this case, we're comparing the two they're same T0s, and that's not significant. So, and then of course, since we found differences in some of them, there's a major difference between the full model and the single model. So that's so you can do this for actually any nonlinear model using the Kimura method. So it's just not restricted to growth curves. Excuse me. You can also do it for multiple groups, but it then becomes, if you find a significant difference in the L infinities, which ones are different? So, I prefer just doing a couple of groups. And to make it a lot easier, in my fish methods package, I provided this function called growth LRT, where you can actually compare more than two groups if you wanted to. And I provided methods, arguments where you can actually use the Monbert, the Gompertz, or the logistic models in there and do model comparison. So all you do is enter your data and then, run it, and then it'll make all the comparisons for you. And then finally, back here, we said, okay, the L infinities are different. the K's may be different, but the T0s are not, but we want to estimate the full model using all those different differences. So I provide this growth multi-fit function too, where you can basically estimate for the groups, the different parameters based on the structure that you found that was significant up above. So it'll provide the full model estimations, and you can use this function to do it. So that's there. And so the GNLS function, let's start with that. So we did using the NLS function by, pretty much by hand. But the GNLS function does this also. And again, you only have to provide the formula. And up here, we're using that Barnbird derivation object. And the way you would set the model up is there's a argument called params, and you list within the list argument there the parameters that you're estimating, and then the classification variable that indicates which groups they should be examining. So in this case, there's a tilde that goes after the parameter. So in this case, if you want to estimate L infinity for both sexes, then it's this L infinity tilde and sex variable. And in this case, this is the full model with 6 parameters. So we're having this categorical variable indication here as before. And then you have to provide starting values, and remembering that this is going to estimate the same way and the same type of model that we just did it in the NLS function, where the first L infinity parameter will be for that first group based in alphanumeric order, and then the deviation from that will be this value following that. So in this case, we need 6 values here. Just remember to keep the same number of starting values for the number of parameters you're estimating. And so you can run this for, this will be the full model. And then when you start fitting models where you're assuming one of the parameters is the same for across the groups, then you just indicate that by using 1 after the tilde sign. You still need all of the parameters you're estimating in this params list, but in this case, to keep it the same across the groups, then using this 1. So you can do that. This is for estimating, assuming the same L infinity function across the groups. Next one is same K. Final one is T0, and then the single model here down below. And you can use then the ANOVA function, do the same thing that we did above. And if you look at the difference between what we did above, there's practically no difference whatsoever, just the 4th decimal place. So you get the same results. So what's ever easier for you? So what do we do about heterogeneity? Again, we could do the weighted least squares using that weighted error variances in the Kimura paper, which is programmed into my growth function. So you could do that, or you could just use the GNLS function, and you can not only can you provide tests for differences in sexes, but you can also explore whether the heterogeneity is different between the sexes. And the way you would do that, in this case, we're showing the variance power function here, and right after the fitted value would put this vertical line with the group after that. And once you do that, you can run and save as an object, and then you can actually compare between models too. So if you wanted to test between, develop this model with parameters for each sex, but wondering if it's just the same parameter in the power functions that you're estimating, you can do the model comparison there too, to determine if you need this a different power estimate for different sexes. And in our case, you can see down below, it pretty much was the same. So if you did the test, you'd find it didn't really. All right, the last thing, I think this is the last thing, well, close to the last thing. So Kimura in 1990 actually provided another paper where he provided the likelihood functions for the different cases we explored so far. One is where we're assuming the population variance or the within group variance is the same across the groups he provided. This likelihoods for those, and this is what you could use to if you wanted to estimate the stuff yourself using like the optimization functions. But he also provided examples in cases where, what if you didn't have equal group variances, and what would that provide? And what I mean by that, if you look at the graph below, here I had two groups, and you can see that the group one in the black has the variances at a particular, the distribution or the variance of the lengths at the same age is much wider for this black group as there are for the red group. So you would, in this case, if you assume that they were equal across the groups, then there's some major issues that can impact there. Whether this actually happens with fish data, I don't know. And I don't know because I don't think people have wondered about it. So I don't think it was ever explored. But in Kimura's paper, he provides these likelihood functions that you can use to explore whether you need, to estimate the sigmas for the different groups. Oops, chat. Oh, okay. Bye, John. I looked for, oops, here we go. So I looked for software that could do this, and there's nothing. And I developed some stuff, and I'll get that to in a minute. So, but before we go, before we move on, I just wanted to point out what happens if you don't correct for unequal variances. On the left graph are type 1 error estimates for these scenarios down here. The truth is that you have homogeneity variances and you estimate, for instance, a GNLS model, assuming homogeneity of variances, but the truth is that there's unequal population variances. You can get these major spikes in type 1 error, which means you're going to find differences in group comparisons more often than there should be. And if you do on the right graph, okay, on the right graph, very similar. If you have the truth is heterogeneity, but you assume, but you're not correcting for that population, you still get these inflations in type 1 error. But it's weird also that if you have if you assume homogeneity of variances, in the cases I explored anyway, the type 1 error actually dropped. So you're not detecting enough significant differences if you modeled in this case. So it definitely affects, again, the type 1 error rates in your comparisons. So I couldn't find a package, so I made a function. It'll be the growth LRT plus function where you can do this. It's similar to the GNLS function, but you specify in this fair structure whether you want to do model the within group variance as equal or unequal. You'll have the error variances homogeneous or heterogeneous, and then you can specify how many those theta values can be estimated. And I also developed a kind of like an ANOVA function. It isn't basically an ANOVA function where you can compare models. And just this is just an example showing the comparisons. Pretty much identical between the GNLS package and the one I I just developed. So that'll be in my fish method package. Just final thing, sometimes some of these assumptions may be slightly violated, and that could, from what I've read, could impact the assumptions of the likelihood ratio tests and their accuracy as well. And so there's another method, and I used once in the past, where you can develop randomization tests, and what this does is you're actually developing what the null distribution of a test statistic should be when there's no difference, and then you can compare it to an observed test statistic to determine if there's any significance. And one of the papers I used way back when was Helser 1996, and he developed this observed test statistics when he's comparing two models, a full model for two groups that has 6 parameters versus the single model with just the 3 parameters. This assumes the same model for the different groups. And essentially it's just using the sum of squares of that single model, and then the sum of squares for individual models fit to the data for each sex. And this is the observed test statistic. And what Helser had done was actually to get the null distribution is to essentially randomize the age length pairs in the data sets he had. But Haddon in his book basically said that that's wrong, because in some of the randomizations you can get, if your ages are small, if you only have like a couple of very old ages, there are times when those ages wouldn't be included in your randomization. So he suggested actually randomizing the lengths within an age across the groups. And the way you would do this, let's say in this example, you have males and females on this little graph on the left for different ages, and the numbers in the boxes, the sample sizes. And what you would do to create the null distribution is you would then take the data within a particular age, mix them up, randomly sample without replacement, and assign the randomized data to back to the original groups with the same sample size. So in our case, you'd have 18. In the first case of age 1, you would have 18 individuals. You randomly pick 10 from the 18 and associate that with back to the females, and then those remaining 8 you would associate with the males. You would fit the new models to those new data for each sex, and you would calculate that same statistic as I showed you, but using the sum of squares from those new models from the new fit data, calculate the statistic, do that, like it should be greater than 1,000 times. And then you get a distribution like this example here. And then you would basically count out of, in this case, we use 1,000, how many values above your basically observed test statistic there are, and you can calculate the probability. And if in this case there's over 27% of the values are over that observed test statistic. So in this case, we're using 0.05. So then there's really no difference, since you had a lot of values above your observed value. So that's the way you would do that. So you could, I don't know the intricacies about what happens with heterogeneity and stuff, but that's something someone could explore. So, and just one last thing, going through all these linear model packages, I did see another package known as generalized nonlinear models. And in this package, you can actually assume other error distributions besides normal, but I've never used it, so I really don't have any advice on what to do with it. But it does have an ANOVA function, so you can do model comparisons and stuff like that. And that's it. And here are the papers. If you want to pull them out, I also have them on PDF, except for the book. So if you're interested, let me know. That's it. Any questions? No, no questions. I'm either really good or really bad. So, Sam, go ahead.
Thanks, Gary. Just a quick question. So in the more complicated models you were fitting using NLS or the other functions, did R ever have any trouble finding the global minimum?
Oh yeah, yeah. Depending on how complicated your structure is, yeah, you can get into some of the fitting issues. So my recommendation there would be to try a bunch of different starting values to see if you could actually find it. Some of the complicated stuff, like having, estimating the theta parameter and the variance power function, that can get a little hairy sometimes too. So yeah, there can be some fitting issues.
And did you find that even with the simulated data that you were using?
Not so much, because it's perfect simulated data. So I know what's going in. So
yeah.
I can
Okay.
say that. Yeah.
Thanks, Gary.
Yep. Anyone else?
Yeah, Gary, this is Alexei. Sorry, I couldn't find the raise hand function.
Okay.
It disappeared somewhere. So could you possibly try to generalize based on your experience of either the data that you worked with or the papers that you read through, in case of the overall fish and, well, maybe some other aquatic organisms? How often are the cases where the residual distributions for length or size are not normal, and the variances are not equal?
Yeah, that's a good question. I don't know, because most people in growth papers just to say, well, we looked at the residuals, they appear to be fine. And no one's really tested or looked for differences, as far as I can find in the literature, has actually looked whether there are differences in the variance across the groups. So that's a really good question. And that's one thing I've always wondered, whether, no one's tested for it because they just aren't aware that they could differ, or that there wasn't a method on testing it. And Kimura's paper is available. I haven't seen anyone really cite that paper for some reason. But it was interesting, because even in that paper, those graphs I showed you with the different bar plots and the type 1 error, he actually provided NEF statistic that's calculated from the likelihood ratio, which actually does better at not having an inflated type 1 error rate. So it's slightly better, which is interesting, because no one's actually ever go back and said, hey, look at this chi-square ratio test is it inflated itself. So I was quite amazed that he had that in the paper and it hasn't been picked up on. So so not bad. I can't really answer your question. Let's put that.
Okay, no, that's fine.
Yeah.
No, I had to ask.
Yeah.
People looked at it. Also, many have noted the correlation between the L infinity and K, right? So you could, So what is your advice how to deal with that? Essentially, you just rely on, the fit of your specified model, Berthold von Bird model, through whatever function and package you selected to estimate your parameters, and you just simply accept it, right? That this is the set of L infinity Ks, and
Yeah. But there's other that's such a I've always wondered about correlations between the parameters, and I was recently reading a bunch of stuff. Kimura mentions that in his paper, where he basically said, if it's not over, correlation's not over 0.99, you have nothing to worry about, which I question. But there is another parameterization of the farm burnt Lamphey function by Bradikowski or something like that, where they it doesn't look like a Von Bert formula, but it has better properties in terms of less correlation in the parameters and stuff. So and Kimura does use this that in his 1990 paper. So there are equations. There is equation like an alternate equation for the Von Bert that has less correlation in the parameters. So if you're interested in doing that, you could use that function. But then you have to convert the parameters and that parameterization back to the original L infinity. The Von Bert parameters were used to the L infinity KT0. So there's things in cases like that. There's some equations that are a little better in estimation properties than the Von Bert.
Mm-hmm.
So, anyone else?
I have one more if nobody else.
Oh yeah, go ahead.
Yeah, so for the purity and glory of science, we certainly could do the testing for the differences in the parameters of growth for, the group A and then group B that, maybe reside north and south of whatever, and you're the one bay, another bay, and such. And there could be some subtle but differences detected. So that's sufficient to sort of report it in a scientific paper. But from practical standpoint, again, how often do we see the situation where the differences in the growth do make difference in the stock assessment, and whether they result in sufficiently different estimates of the population biomass or effect reference points, etc. Again, could you sort of summarize, generalize?
Oh boy, I don't know if I can do that. I know there are cases where there's definitely some growth differences, and of course, if the fishery's selecting a different size, you could potentially protect one sex, let's say, over another, and that could be, issues with, determining, as you said, this the SSBRs or whatever. But offhand, I can't.
Okay.
I don't have an example offhand where.
Okay. So here's an idea. I didn't have a chance to read the document that you sent this morning, but I think it would have been really useful to have an example where you would take either better real data from somewhere, from some study, but if not, then simulate it and just go through step by step to sort of demonstrate, everything that you talked about today, and show how that in the end results in or affects and it produces the differences, and our estimates of the population size, so population growth rates, vital parameters that affect reference points, and possibly catch advice. And that could be extremely useful, so that people can see
Yeah,
Well,
we could do that in a future seminar. So
yeah, that'd be great.
yeah.
Thank you. That was very good. Very
Yeah.
cool.
Thanks.
A lot of information.
That's why I sent out the slides. Any other questions? No. All right. Thanks, everyone. I'll send out an email probably after the holidays with the next announcing the next seminar. So again, if anyone out there who uses R and is interested in giving a seminar, let me know. All right. Well, have great holidays, everyone. Talk to you later.